What if I were able to take these grains of sand, drop them into this hat, and with the tap of a wand, multiply them by 1,000,000,000? You'd call me Lord Voldemort, just with a more defined nose. How is this actually possible? It's not with sand, a hat, or a wand, but through the process of bacterial transformation, and with genes, proteins, and bacteria. What better place to discuss bacterial transformation than bacteria-ridden New York City? Bacteria replicate very rapidly, and by using this, we can, through insertion of genes into bacteria, mass produce one of the building blocks of life, proteins. This is bacterial transformation. Come, dive in deeper with me. In order to start the process, we must first open up the bacteria.
You see, bacteria don't take too kindly to form pieces of DNA trying to get inside them. And pieces of DNA like our gene are blocked by the bacteria's cell membrane. Any sane person will just let the bacteria be. However, scientists are far from sane and force them to open up through the process of electroporation. Here, a pulse of electricity is directed into a colony of bacteria which creates small holes or pores in their cell membranes.
Once pores are made, the gene can enter the bacteria. However, the gene needs a vector or mode of transportation in order for the bacteria to accept it.
One of the most commonly used vectors is a plasmid. A plasmid is a circular segment of DNA commonly found in bacteria. In order to place a selected gene to a plasmid, the plasmid must have a section of a cutout, and then the gene inserted into that spot. In order to cut the plasmid, a restriction enzyme is used. You can think of a restriction enzyme as Pac-Man. He comes and he chomps down the DNA, cleaving it at certain locations. There are variations in the type of restriction enzymes, and each one cuts DNA in a specific way. You then select the restriction enzyme that cuts the DNA in such a way that the ends of the plasmid will match and attach with the ends of our selected gene. We must also add a gene for antibiotic resistance into our plasmid, which is important to we will see later. Once our selected gene is combined with the plasmid, it can hitchhike into the bacteria.
However, this begs the question, how do we know which bacteria in the colony took in our plasmid? This is where the gene for antibiotic resistance comes in. Antibiotics are put into the colony and attack all the bacteria. Only the bacteria that took in our plasmid with the antibiotic resistance gene will survive.
You can think of this as a game of rock, paper, scissors. All the bacteria in our colony at the start are paper bacteria. Then, our plasmid is introduced and transforms all the bacteria enters into rock bacteria. Our antibiotic is scissors and beats all the paper bacteria that did not take in our plasmid, but it loses to all our rock bacteria which did receive the plasmid. The result is a colony of bacteria that all have our plasmid in them.
From there, it's as easy as a layup. The colony of bacteria is put into a growth medium full of nutrients. They use information in our gene to create the protein of interest. As the bacteria colony grows exponentially, so does the amount of our protein. Once the bacteria colony dies, the proteins inside them are released. And through filtration, we can get a solution of solely the protein of interest. This process has been used for many drugs and vaccines, and its abilities in terms of mass production have driven costs down, bringing new hope to many.